Hello everyone, this is Professor Roman. Let's continue the field theory lectures. We've been talking about simple algebraic extensions, and the multiplicativity of degree does lead to an interesting fact about minimal polynomials and intermediate fields. So let's talk about that. As shown in this figure, suppose that Fe is a field extension, F is the base field, here's E at the top, and that alpha is an element of E that's algebraic over F. So here is F with alpha adjoined. So this is from F to F of alpha adjoined is a simple algebraic extension. And suppose further that K and L are intermediate fields between these two fields, F and F with alpha joined, and that the minimal polynomial of alpha with respect to K and L is the same. So I'll call it M of X. That means the coefficients of M of X lie in K and also in L, and so they lie in the intersection. Moreover, since M of X is irreducible over K, it's also irreducible over a smaller field, K intersect L, and so we can add the fact that M of X is the minimal polynomial of alpha over the intersection. Therefore, the degree of M of X, which is the same as the degree of F of alpha joined over K, and the same as F alpha joined over L, is also equal to the degree of F alpha joined over the intersection, and everything is finite. And therefore, by a degree argument, which I'll leave for you, K is equal to K intersect L. And similarly, there's a symmetry here. L is equal to K intersect L. So K and L are equal. So the upshot of this is if the minimal polynomials of alpha over K and L are the same, then K and L are in fact the same intermediate field. Okay, so that's the statement of this theorem. And therefore, distinct intermediate fields have distinct minimal polynomials. That is to say, more precisely, if the distinct intermediate fields between F and F of alpha, say one of them is called K, then its minimal polynomial of alpha over K is distinct from the minimal polynomials of alpha over other intermediate fields. But all of these minimal polynomials of alpha over the various intermediate fields divide the minimal polynomial of alpha over F. And you should pause to understand that. Think about that for a minute. Therefore, there are only finitely many intermediate fields in this extension. So a simple algebraic extension has only finitely many intermediate fields. The converse, for finite extensions, the converse is also true. So, a finite extension, Fe, is the simple extension if and only if Fe has only finitely many intermediate fields. So because of the theorem we just proved, that takes care of half of this theorem. We only need to prove that if Fe has finitely many intermediate fields, then it's a simple extension. Of course, if E equals F, if the extension is trivial, then there's nothing to prove because E is a simple extension It's f with any element of f adjoined. So we can assume that this is a proper extension. Also, if f is a finite field, then so is E, because E is a finite dimensional extension of E. And in this case, we had a theorem quite some time ago, theorem 1.3, that tells us that E star, this is the non-zero elements of E, is a cyclic group under multiplication. And so if alpha generates that group, then E is f with alpha adjoined, and so it's simple. So we're left with the more difficult case. F is an infinite field. Now, since Fe is finite, the extension is finite, finite dimensional, it's finitely generated, for example, by any linear basis for E over F. So we can look for, among all finite sets of generators for E over F, we can find one of smallest size. And let's say that's alpha 1 through alpha n. So E is f with alpha 1 through alpha n adjoined, but if we remove any of the alphas, then the resulting field here is a proper subfield of E. So no set of size less than n generates E over F. Now if n is 1, then we're done. We have a simple extension. But if n is bigger than or equal to 2, then we can consider these intermediate fields, F with alpha 1 plus A alpha 2 adjoined, where A is an element of the base field F. So as A varies over F, remember F is assumed now to be infinite, we get infinitely many different elements, alpha 1 plus A alpha 2, but there are only finitely many intermediate fields, which means there must exist two elements of F, distinct, A and B, for which these two fields are the same. There's a lot more, but all we care about is 2. There are infinitely many of these fields, but they're potentially, but there can only be finitely many intermediate fields. So some of these, a lot of these have to be equal. So I'll call this K. Now in K, we have both these elements. And so, for example, their difference is in K, and you can do the algebra here, the elementary high school algebra. Alpha 1 and alpha 2 must also belong to K, which means F with alpha 1 and alpha 2 adjoined is contained in this field. This is K. But this is clearly contained in here, and so these are equal. And therefore, E, which is F with alpha 1 through alpha n adjoined, is also F with these elements adjoined. But there are only n minus 1 of these. And that contradicts the minimality of this generating set. And so n cannot be bigger than or equal to 2. And this extension is simple. Okay, this is a clever argument, something you probably wouldn't think of at first. It's worth going over until it seems clear, even though it may not be clear how it was discovered in the first place. This theorem does provide some insight into the Tower property for the class of finite simple extensions. if we have a finite simple extension and an intermediate field K, then both steps in this tower are finite and simple. The upper step, K, F with alpha joined, is the same as K, K with alpha joined. And this is finite. Since the full extension is finite, both steps are finite. Okay. But because the upper step can also be written this way, it is simple. The lower step is finite. And here's the interesting point, really. Since the full extension has only finitely many intermediate fields, so does the lower step. And so the theorem we just proved applies and shows that the lower step is simple. So 1/2 of the tower property holds for finite simple extensions. If the full extension is finite and simple, each step is finite and simple. The other half is the issue of whether, if we have a tower where both steps are finite and simple, is the full extension also finite and simple? It's certainly finite, again by multiplicativity of degree, but the question is it simple? Can F with alpha joined and then beta adjoined be written as F with a single element adjoined? Not necessarily. And here's an example. Consider this tower of fields. The x and y are distinct, independent variables. We have z2 with x squared and y squared adjoined. That's the base field. The big field is z2 with x and y adjoined. Intermediate field, z2 with x squared and y adjoined. So this tower can be written, here's this same base field. First we adjoin y, and that will give us this field. Then we adjoin x, and we'll have this field. So each step is simple. Now y is a root of this polynomial, t squared minus y squared, over the base field. And so the lower step here has degree 2. It's a proper extension, so it doesn't have degree 1, so that means it must have degree 2. Sorry, I got a little problem here with separating pages. A constant frustration. Okay, and similarly, x is a root of t squared minus x squared, which is a polynomial in T over the intermediate field. So the upper step has degree 2. And therefore the full extension has degree 4. But if alpha belongs to the big field, then it can be written as a rational expression in xy and xy, where the coefficients lie in the base field. And since z2 has characteristic 2, all the cross terms, if we square this, all the cross terms are multiples of 2. In other words, there's 0. And so beta squared, for example, then is just a squared plus x squared b squared plus c squared y squared plus d squared x squared y squared. And similarly for gamma. And so alpha squared belongs to the base field. That means that all the elements of the big field have degree at most 2 over the base field. You cannot generate an extension of degree 4 with elements of degree 2. And so the full extension is not simple. This example's a little testy. You might have to go over it a little bit. You can see that even simple extensions aren't necessarily simple. Okay. Now we're going to return to this issue. Despite this example, we will have more to say about when the full extension of a simple tower is simple. There's a famous theorem called the theorem of the primitive element that we'll discuss a little later in the course. All right, so we've said a fair amount about simple algebraic extensions or simple finite extensions, same thing. We know that finite extensions are algebraic, but algebraic extensions need not be finite, and that's something for you to find. You can find an example. But finitely generated algebraic extensions are finite. And that's what we want to explore now. A finitely generated extension looks something like this. Alpha 1 through alpha n are the generators. And as I discussed earlier in the course, that can be this extension can be decomposed into a tower where each step is simple. And that's often a very useful thing to do. It will help us prove the following. The following are equivalent for an extension Fe. Fe is finite. Fe is finitely generated and algebraic. Fe is finitely generated by algebraic elements, meaning that just the generators are assumed to be algebraic. If that's the case, if these three hold, then this field, F with the generators adjoined, consists merely of the polynomials rather than the rational functions in alpha 1 through alpha n over F. And each alpha I appears only to powers less than the degree of the minimal polynomial of the element alpha I over F. So that's a nice characterization, simplifies the characterization of F with alpha 1 through alpha n adjoined. Okay, so finite, finitely generated and algebraic, finitely generated by algebraic elements, all equivalent. Well, if Fe is finite, then it's both algebraic and finitely generated, again, by a basis for E over F. This is a linear generation, but we can just take it as being ordinary generated by the basis. Every element is a linear combination of basis vectors, but basis elements, but we can think of it simply as field generation. If Fe is finitely generated and algebraic, then it's certainly finitely generated by algebraic elements. So we said that 1 implies 2 and 2 implies 3. Finally, if Fe is finitely generated by algebraic elements, say E looks like this, then we use this tower here. Each step in the tower is finite because the whole because the whole extension is finite. I'm sorry, I didn't say that right. Each step in the tower is finite because it's simple and generated by an algebraic element. And therefore, by multiplicativity of degree, the entire extension is finite, the full extension. So that's 3 implies 1. As to this statement, well, since the generators alpha I are algebraic over F, we know that the simple extension F with alpha 1 adjoined is the set of polynomials in alpha 1 over F, and their degree is restricted, the degree of alpha 1. Also, F with alpha 1 and alpha 2 adjoined, being a simple extension of F with alpha 1 adjoined, is a set of polynomials in alpha 2 over F alpha 1, or in other words, whose coefficients are polynomials in alpha 1 over F. And again, we have this degree restriction. So you can probably see, if you think about it for a minute, that the elements then of F alpha 1 alpha 2 are polynomials in alpha 1 and alpha 2 over F, and the degree requirements obtain. And so, continuing this argument, you can see this field consists of the polynomials in alpha 1 through alpha n over F, where each alpha I appears only 2 powers less than the degree of its minimal polynomial over F. This is a little bit informal. You might want to practice making that a little more formal. You could use induction, for example. Okay, so the important takeaway here is that if FE is finitely generated by algebraic elements, I think I referred to that as algebraically generated. You'd have to say finitely algebraically generated. That's a little awkward. Then it's algebraic. If the generators are algebraic, then the field is algebraic, the extension. And finitely generated algebraic extensions are actually finite dimensional. As for the distinguished properties, the class of finite extensions, or the class of finitely generated extensions, is not closed under arbitrary composites. That shouldn't be too surprising. If you're allowed arbitrary composites, you're not going to be able to maintain finiteness. And here's an example which is actually coming up a little bit later, but I'll mention it now. We're going to show that for distinct primes, P1 through Pn, the field of rational numbers with their square roots, the square roots of the primes adjoined over Q. If there are n primes, this has degree 2 to the n. And so this extension is algebraic. This is the extension where we adjoin all of the square roots of primes, the square roots of all the primes. This is algebraic, and that too will be coming later, but it's neither finite nor finitely generated. But this is the join of these individual simple extensions of Q So these fields are finite and finitely generated, but their arbitrary join is neither finite nor finitely generated. So neither one of these classes, the finite extensions or the finitely generated extensions, is strongly distinguished, but they are distinguished. Okay. So let's take a look at the proofs of that. Let Fe be an extension. The class of finite extensions is distinguished, but not strongly distinguished. Also, this is something we'll need later. If B is a finite basis for E over F, and if K is any extension of F whatsoever, then the basis for E over F will span the composite EK, not over F, but over K. And so this degree is less than or equal to this degree, because a basis here is a spanning set here. So another way to say that is that lifting, which we did here, the lifting of EF by K is EKK, cannot increase degree. When you lift, you cannot increase the degree or the dimension. You can certainly reduce it. Okay, as to proof, the multiplicativity of degree shows that the class of finite extensions has the tower property, and I'll let you fill in the details. As to lifting, if B is a basis, say alpha 1 through alpha n, basis for E over F, then E is F with alpha 1 through alpha n adjoined. But as we've seen, the elements of E are in fact polynomials in alpha 1 through alpha n over F. And each alpha I is algebraic, and therefore over F, and therefore also over K. So it follows that EK is K with alpha 1 through alpha n adjoined, and again, because these are algebraic over K, this is the set of polynomials in alpha 1 through alpha n over K. Therefore, every element beta in EK is actually a polynomial in alpha 1 through alpha n over K. Each term in beta has this form. It's a product of powers of alphas with coefficient A belonging to K. But this monomial, without the coefficient, is an F linear combination of alpha 1 through alpha n. And so with the coefficient, this is a K linear combination of the alphas. And so beta itself, the polynomial, is a K linear combination of alpha 1 through alpha n. And that means these elements actually span EK. And that's where we get this result. Later in the book, in the course, much later actually, we're going to be able to prove that if the extension Fe is sufficiently well behaved, that is to say, if it's finite, normal, and separable, then the degree of EK, KE, over K actually divides the degree of E over F. All we can say now is that it's less than or equal to. As to finitely generated extensions, the class of finitely generated extensions is distinguished, but again, not strongly distinguished. As to the tower property, if we have a tower here where each step is finitely generated, so S and T are finite sets, then because the join F with S adjoined followed by T adjoined is the same as F with S union T adjoined, the full extension is also finitely generated. Conversely, if a full extension is finitely generated and K is an intermediate field, then of course the upper step, which can be written KS, is finitely generated by the same set S. And the interesting thing now comes up. The proof that the lower step is finitely generated is surprisingly difficult. In my first draft of this book, I wasn't even going to prove it. But after writing chapter 3 on transcendence, I was able to give you a proof. So it's going to be a while before we can prove that the lower step here is finitely generated. So we'll just accept it for now. For closure under lifting, if E is F with S adjoined, again where S is finite, and if K is any extension of the base field F, then EK is K F of S, which is KS. And so the composite is finitely generated over K, again by the same set S. Field theory plays a significant role in several areas of mathematics. Coding theory, for example, cryptology, algebraic geometry, and so on. Also number theory. And here is a prime example. Let P1, P2, and so on be the distinct primes, in any order, it doesn't matter. Then each square root of a prime is algebraic over the rational field, and so if we adjoin the square roots of several primes to the rational numbers, this set is just the set of rational polynomials in these square roots. What we want to show is that the square root of Pm plus 1 is not contained in the field you get by adjoining to Q the square roots of other primes, P1 through Pm. Or another way to say it is that this field has degree 2 to the m over the rationals. So for example, there's no way to write the square root of 7 as a rational polynomial in the square roots of 2, 3, and 5. It would be interesting to try to prove this directly by simple algebraic means, but as you'll see, it's not terribly difficult with a little knowledge of field theory. So first we have a lemma. If P1 through Pn are distinct primes, then a non-zero polynomial, in other words, a non-zero element f of this field, whose square is rational, must be a monomial, a single-term polynomial. And the proof is by induction on the number n of primes. For the basis step, if n is 1, then f belongs to Q with square root of P1 adjoined, so it's a polynomial in the square root of P1, so it looks like this. A and B are rational. So we square both sides. Now f squared is rational by assumption. A squared is rational. B squared is rational. So in order for this to be true, AB has to be 0. If A is 0, then f is b, which is rational. So f is a monomial. It's a constant polynomial. If b is 0, then f is a square root of p1, which again is a single-term polynomial. So that takes care of the basis step. So let's assume that this result holds for n or fewer primes, and suppose that f belongs to the field Q with the first n plus 1 primes, square root primes adjoined. Just to keep the language down, I'm going to call this the larger field. And if we stop at Pn, I'm going to call that the smaller field. Okay. So we assume f belongs to this larger field, and we assume that f squared is rational. If f belonged to the smaller field with only n primes, then the inductive hypothesis applies immediately, and we know f is a monomial. So we can assume that f does not belong to the smaller field. That means f has this form where a and b belong to the smaller field, but a is not 0, because if a were 0, then f would be b, which would belong to the smaller field. Square root of Pn plus 1 does not belong to the smaller field, because then f again would belong to the smaller field. Squaring this gives this expression, this equation. A and b belong to the smaller field. F squared is rational and so belongs to this field. So f squared, this term, and this term belong to the smaller field. Square root of Pn plus 1 does not belong to the smaller field. Therefore, AB has to be 0. And since A is not 0, B has to be 0, and F is equal to A square root of Pn plus 1. Squaring that gives F squared equals A squared Pn plus 1. So A squared is rational. And so now we have A belonging to the smaller field, A squared being rational. We can now apply the inductive hypothesis, implying that A is a monomial, and therefore so is F. Now we can prove the main result, which follows pretty easily from the lemma. For distinct primes P1 through Pn, square root of Pn does not belong to this smaller field, Q with square root of P1 through square root of Pn minus 1 adjoined. Or equivalently, this degree formula holds. Well, for any n bigger than or equal to 1, if square root of Pn should belong to this field, then since the square of this left side, the square of square root Pn, is rational, the lemma applies and tells us that the square root of Pn is a monomial over this field. And so square root of Pn is a rational times a product of some of these square roots, maybe all, but not necessarily. This is a one-term polynomial in these guys. But then, if we square, we get Pn is Q squared, which is rational times a product of primes different from Pn. And this, of course, is false. So this cannot happen.